Hello everyone, I am Alok Kumar and I welcome you to the third lecture on monotonicity and maxima and minima. Already we have seen the definitions of monotonicity, strictly increasing and decreasing, and we also have seen some applications. So now is the time to go for me to the again revising the lecture that I have done yesterday and then go to the maxima and minima topic which we will cover today. So let me now share my screen with you all first. Okay, so one of the applications that we have to do before going to maximum minima is this one, that we already have done what it means to be strictly increasing or decreasing. Now one application is called establishing inequalities. So we will do like this, that we'll just let me choose a color and go. Okay, so if I want to establish, if you want to establish, so establishing inequalities, that means that, as an example, let me take 2 sine x plus tan x greater than or equal to 3x, and you have to prove it for each x that belongs to the interval 0 closed and pi by 2 open, because tan pi by 2 is not defined. Now there are a lot of problems like this, and for all of them we have got a sure method. First we designate a function, define a function f of x. So move everything to the left side or right side. So let me move to left side. So I propose the function 2 sine x plus tan x minus 3x. Now let me look the derivative of this function. So f prime is twice of cos x plus sec squared x minus 3. Now if this is my f prime, let me see the sign of f prime, that how f prime changes its sign. Derivative changes sign, the points where it changes. So I can write here 2 cos x over cos x squared x minus 3, everything in terms of cos squared x. So I can write 2 cos cube x minus 3 cos x plus 1, and upon cos cube x. So you will note this. Let me erase this for a better view. So this is cos square x. Now let us do some background work. This is 2u cube minus 3u plus 1 if I let u equal to cos of x. Obviously this has a root. Obviously this has a root at u equal to 1. So what I can do is I can take common. So this is u minus 1 and times, as I told earlier, this is 2u squared. Worry about this one, that is negative of 1. And this is plus some au. This I can find easily by equating coefficient on both sides. Say coefficient of u squared, which is 0 on the left side, means here. And on the right side, u square coefficient, this u will give a, this will give me minus 2. So a equals 2. So it means I can write this as u minus 1 and 2u squared plus 2u minus 1. Let's check. So you are getting here 2u cube, and then you are getting this one and minus 1. So 2u cube minus 3u plus, that was not 1. So there is one small, this one gap here. So this is in fact 3, as you can check here. So this is 3. So this is 2 cos cube x minus 3 cos x, and this is plus 1. This is already 3 cos x plus 1. This 3 comes here, that is 3 cos x. Rather it is 3 cos square x. So we have to consider not this, but we have to consider another one. So let me consider not this, but something different. That is, let me do on the same page so that we can keep track of it. So it's like 2u cube. So it's not this, it's 2u cube minus 3u square plus 1. Still it has 1 as a root because it vanishes. So u minus 1, 2u square, and let me write this bu, and this is negative of 1. So coefficient of u is now 0 on the left side. On the right side, this u gives you a negative of 1, and this gives you negative of b, that is this one. And so you get 1 plus b is 0, so you end up with b equal to negative of 1. So you will get u minus 1 into 2u squared minus u minus 1. Again, u equal to 1 is a root, so I can write u minus 1. This is factorized by quadratic, and this is 2u, and 2u after that you can have 2u. So it means what you have done is we have written is as cos x minus 1 whole square, that's important, whole square, and you get 1 plus 2 cos x over cos square x. Now because my x belongs to 0 to pi over 2, look at the interval. It means all things are non-negative. Cos x can be of course 1 at 0, so it is non-negative. So f prime is non-negative, but I told you that even if f prime is 0, the function is still can be strictly increasing, provided f prime equal to 0. The points don't form, they don't form interval. So that it does not, because it has got like isolated roots or what is called discrete roots. So f prime is non-negative, and so we can say that f is strictly increasing. Means that for x greater than 0 or x 0 to pi by 2, 0 to pi by 2, we can say that f of x greater than f of 0 if x greater than 0. This I can say. With this, I know that f0 is 0 because we have defined fx as 2 sin x plus 10x minus 3x. So obviously f0 is 0. We already got it. And so we'll write that f of x greater than f0. But remember, at x equal to 0, f0 is 0. We combine these two. Once we combine these two, we get f of x greater than equal to 0. And for all x, that for each x and belong to 0, closed, and pi by 2 open because it is not defined at pi by 2. So this is an example of saying that how you can use monotonicity or the ideas of strictly increasing and decreasing in establishing some inequalities. They are quite regular in examination. Sometimes you may be asked that of the following choices, which is correct? This function is strictly increasing in the interval or decreasing the interval, or order relation, which is greater, which is smaller. So please keep all these things in mind, those who are preparing for JEE Advanced. Okay. Now that we have done this, we can go and start maxima and minima by giving some definitions first. Normally, students have difficulty in definitions. So I will write definition very clearly so that you can see also. So first is absolute maximum, and of course minimum I will define analogously. So let's just write. So I am defining absolute maximum, absolute. So that's a technical term. Absolute we call, or we call sometimes global maximum. So the definition, as you know, definition is the most important part of discipline of maths, especially calculus, because if you don't understand definition correctly, it may be source of many errors. So it says like this, that let f d to r. So let f d to r be a function. So listen very carefully. Let f d to r be a function, and we say that f is said to have an absolute. Remember the word an. I'm writing an, not the. It is said to have an absolute maximum on D if there is at least one point C, that in D means C belong to D, there is one point C in D such that f of x less than or equal to f of c for each x that belongs to D. So let us review what I said, that let f d to r be a function. Nothing great about it. D is the domain, r is the codomain, or anything function defined on. D may not be the full domain, no, in the sense that we may restrict it to some other function. So let's say f d to r be a function. D, of course, is a subset of r. We are doing real calculus, and if it's said to have an absolute maximum on D, if there is at least one point C in D, C belongs to D, such that f of x less than or equal to f of c for all x belonging to D. Similarly, we can define absolute minima by just taking here this one, that we will just say here, let me change the color and show you the contrast. So I can just change and I can say that if it's said to have an absolute, here I can change absolute minimum on D if there is at least one point C. So at least one point C, or I will write at least one point D in D, such that here I will write such that f of D, or let's write f of x only first to maintain the notation. So we can write this only first. So such that f of x greater than or equal to f of D. Then we will say that it has absolute minimum at D. Now, let me draw a graph that will picture it. So suppose I draw the usual known curve. So one, I'm drawing the graph of, it is f of x equal to sine of x, consider, on the interval 0 pi, both closed. So 0 and pi. And one, I am just defining a function like this point is say 2, and I'm saying this is 0 reason. So I'm writing f of x is 1 over x, 0 less than x less than equal to 2. And at 0, I will say I will define f of x is 1 when x equals 0. That is at 1, at 0, that function, because 0 it is not defined, this does not go. So 0, I will say that, okay, this function is just 1. So this is like 1. Here, it is not defined at 0, this branch. So this is x equal to 0. Now for this function, this number, this becomes absolute minimum. Now here, this is nothing is there. See, this is going on and on, because if 0 plus, if you write 0 plus, it will go to infinity. So we will say here that no absolute maximum. Very important. Absolute maximum is not there. Absolute minimum does exist. Here, absolute minimum, this point, absolute minimum, and this top, this peak is absolute maximum. Apply the definition. The definition says that if you find some interval around D, means there is some point in C such that f of x less than or equal to fc for all x element of D. It means, see, you have found a point C here, C, namely pi by 2, such that f of pi by 2, here f of pi by 2 exceeds or equal every value that you can think of in this interval. So it is the largest in this interval, and so it is the absolute maximum. This is absolute minimum. You cannot go down than this. This was absolute minimum. Now that tells you why n is used. This function attains its absolute minimum at 2 points. In general, the function may attain absolute minimum at infinite number of points. That is perfectly justified. Definition does not preclude that. It does not say that no, we cannot. You can attain. They are saying an absolute minimum. But of course, all the values must be same. Means while absolute minimum value remains same, it can be attained at even infinitely many points. And so it is called an absolute minimum. In the example on the right side, fx is 1 over x. Here at 0, of course, you are saying it is here. And so it is 1. You are seeing that there is no absolute maximum. Because when x tends to 0 plus, then the function goes to infinity, it just blows up. And so it does not have a absolute maximum, but it does have an absolute minimum, and that happens as at 2, that is 1 over 2 this height. So it has absolute minimum. I can take one other example, fx equal to x, the very simple created example, fx equal to x. And suppose I write like this. So I write fx is x, 0 less than x less than 1. So this is 0 and this is 1. This function, I will say, this is no absolute maximum and this is no absolute minimum. Means this has neither absolute maximum nor absolute minimum. Many times students make the mistake that they say that the absolute value of this or the global maximum is 1. That's not true. The value 1 is not taken by function. Means there is no c such that fc equals 1. This c does not exist. This c does not exist. You can say that the function takes the value as close to 1 as possible, as close to 0 as possible. All these are fine. But if you are asked that does the function have an absolute maximum, answer is no. Make no mistakes. Does the function have an absolute minimum? Again, answer is no. So these things are okay. On the contrary, suppose the same function, if I tweak around, if I change little, and I write f of x is x, and I define on 0 less than equal to x less than 1, then you will say that this function has got absolute minimum but no absolute maximum. So we can keep changing and we can get our observations. So we covered till now absolute maximum, absolute minimum. One warning is in order, so I'll write as remark. In the definition of absolute maximum or absolute minimum, we just said f is a function, f d to r be a function. We need not say if it is continuous or something. So so not even differentiable, right? So we did say f is just a function. It means that a function may have a discontinuity and still at that point it may have absolute maximum. That is fine. Say for example, I draw a curve like this. I just make up a curve. So I write f of x is modulus of x, and suppose I restrict it to -1 less than equal to x less than equal to 1. This is this, and I say that this is not, and x is not 0, this one. And so at 0, I define it at 0, it is 0, it is 4. Means that this is -1, this is +1. This height are both 1. At 0, suddenly the height is much more. It is like here. This height is 4. So now at origin, the function attains the value 4. And you see that nowhere does it achieve a height more than this one, the height 4. And so we will say that this is absolute maximum. Means the function does attain an absolute maximum at the point origin. The value is given by 4. So even discontinuous functions also can have these things. And that's why in definition we just spoke about the function, not even continuous or something. Of course, continuous functions constitute a very important class as far as application is concerned. And so we will have a good theorem. We'll have something to say about it just after some time. Next is this one. Other definition is the thing is relative maximum. This also is confusing to student. Relative maximum and similarly relative minimum. Relative, which we can also call local. So this is like relative. So we discussed absolute. So absolute, or we call global, or here we say relative. So we say relative or we say local. So global is the antonym for local and relative for absolute. So they are just pure English words, nothing maths about it here. Now, this is local maximum, local minimum. So we will say that again f d to r is a function. So f d to r is a function. Then f is said to have a relative maximum at point C in D, so point C belonging to D, if there is some interval, if there is some interval I, we talk of interval, if there is some interval I, of course containing C or around C, if there is interval containing C such that f of x is less than or equal to f of C for all x that belongs to I intersection D. This is important, not just I intersection D. You will find out that why we have defined like this to take care of some important case. So we say that f is a function from D to R, then f is said to have a relative maximum at C, element of D, interval I containing C, such that f of x less than or equal to f of C for all x that belong to I intersection D. Similarly, we can define relative minimum, and we will say that f of x greater than or equal to f of some D for all x that belongs to I intersection D again. Let me put this in action and one example let me take. So this is some graph I am drawing of a function. So we'll write the function also. This is origin passing, and this like tangent is like going like this. So let us write this point. This is suppose minus 1 over 2. This is 2. So I will define a function f of x as x 1 minus x whole squared from negative half less than or equal to x less than or equal to 2. Now, if I define like this, then this function is defined on closed and bounded interval minus half to half, this one. Now, at 2, this function by definition, this point is a point of absolute maximum, no doubt about that. It follows from the previous article. But it also is a point of relative maximum, because around this point I can find an interval, say interval this. So this is I and D was here, so I intersection D means it is just this interval I intersection D here, means right side not available but left side you have available. And so this makes sense. Had I said I, then it would not exist. So I said I intersection D, means get an interval around this point, an intersection of this interval with the domain. If on some part this function, this is the highest value, then it will be called absolute maximum. So it will call relative maximum. So it is true relative maximum, and absolute only we defined before. So relative is here, we are right now defined. Similarly, this here we have both sides available I, this side also, this side also. Now this is the point of relative minimum. This is again a point of relative minimum, also absolute minimum, and this point is nothing but relative maximum. So it means what we have found is, this is of course not absolute maximum. So what we have found that this point corresponds to both absolute maximum also as well as relative maximum. This is relative minimum, this point relative maximum, this is relative minimum, absolute minimum. In general, every absolute maximum or every absolute minimum is also in particular a relative maximum or relative minimum, means every absolute extremum again, the word we used for both. So we say minimum, we want to club together minimum or maximum. So every absolute extremum is in particular a relative extremum, means every absolute maximum is in particular a relative maximum, and every absolute minimum is a relative minimum. So these are the two definitions. Now let's talk about one very important stuff, that is critical points. Critical points. You are asked in JE questions on what are the critical points or how many critical points. So now critical points are defined like this. So let's say that we have got again function d to r. So let me change a color one more time if we're getting this one. Okay, f d to r. Now f d to r be a function. So this is still is a function where d is of course subset of r. We are doing calculus on real number line. So f d to r be a function. And then we will say that a point C that belongs to D is called a critical point. Is called a critical point. Critical point if critical point of function if first C is an interior point of D, means it is this one. Suppose interval is 2 comma 4, then 2 and 4, they are called boundary points. They are called boundary points, means here is not interior. 2 comma 4 open interval, every point is interior. 2 is of course not a point interval, so every point that belongs to this interval is an interior point. So we make a distinction, useful distinction. So see, interior point of interval D or this one D. Second is f prime C equal to 0 or f prime C does not exist. Means all those points where f is not differentiable, and if differentiable, then f prime must be 0. Means either f is not differentiable, or if it's differentiable, then derivative must be 0. So these kind of points which lie in the interior of D, they will be called critical points. The usefulness of critical points is this, that there is a theorem called extreme value theorem. Name goes like extreme value theorem for continuous function on closed and bounded intervals. So it is very fundamental theorem. If a comma b to r and f is continuous, so it concerns only continuous functions right now. So we are saying the name only tells what work it does. Extreme value theorem for continuous functions on closed and bounded interval. So we are saying that let f a b to r be a function. And next we are saying that if f is continuous, then we know that f is bounded and f attains its bounds. That is, f has both an absolute maximum, and absolute minimum attained at some points of D. Of course, attained at some points of D. Means there are some numbers Rs element of D such that f of r is the greatest value or absolute maximum, and f of s is the least value, we say sometime, or we say absolute minimum. Means the theorem says in brief that a continuous function defined on a closed and bounded interval attains its bounds. So that is good one. And how you construct it, that what we do, steps we do, that we find all critical points of f and endpoints of domain So say critical points are say C1, C2, many Cn. Normally they are few in number. They are few normally. They are few normally. And endpoints D call AB. And then we tabulate, we calculate values f of A, f of C1, f of C2, f of C1, and f of B. So we make this table. We make this table. And out of these numbers, finite numbers, they are all finite. So many numbers can be there. So all of them, whatever is greatest. So the greatest number is absolute maximum, and the least number is absolute minimum. So that's what we say. So this is the method for finding the greatest and least value, or say absolute maximum and absolute minimum for continuous functions, because we know it is attained. So let us review it with the help of an example. So one example is in order. So let's define a function f -1 to r given by f of x. This is a beautiful problem. Fx is negative of x. For conceptual clarity, 1 less than equal to x less than equal to 0. In fact, -1. And then 2x cube minus 4x square plus 2x, 0 less than x less than equal to 2. So you are seeing that the function is defined on -1 to 2. At 0, the 0 is in this branch, not here. So now I want to find first critical points. My job is to find critical points and also absolute maximum and minimum. This question makes sense. This makes sense, means can be answered. As f is continuous, you will find that f is continuous. We will actually prove f is continuous, to be proved without effort. And then it is defined on closed and bounded. That is -1, 2. So we know before even if we begin that yes, these claimed values, absolute maximum and absolute minimum, will of course exist. So we do like this. First find critical points. So let's differentiate this. F prime. So f prime will give you negative of 1 for there is nothing on the left side. So -1 less than equal to x less than 0. Here equality is not there right now. No, this is not there. Open. Now because it's differentiable, and 2x cube I differentiate. So 6x square minus 8x and plus 2. And this number is still from 0 to 0 less than x less than equal to 2. Again, same remark, 0 is not included because here this is not there. So these functions are like this. So f prime is this. So f prime 0 we do not know. This we can factorize. This we can factorize. 1 is a root, you can check. 1 is a root. And 2 I can take out. This is 2 into 3x square minus 4x plus 1. So that is 2x minus 1 and times 3x minus 1. So this is just a little factorization. So this I got. And I want to know f prime 0. This one. To answer this question, I need to know f prime plus 0, right hand derivative at 0. I want to know left hand derivative, f prime -0. These two I want to know. If they are equal, then f is differentiable at 0. Otherwise, it is not differentiable or does not exist also. So again, two methods. First method that I have emphasized very much in my teaching. First method, by definition. So by definition, you will say that f prime plus 0 is limit h tend to 0, f of 0 plus h minus f of 0 upon h, limit h tend to 0, f of 0 plus h. Okay, when you look up 0 plus h, then your function is here minus h. So we are writing here negative of h, and f0 is from here, f0 is 0, so minus h minus 0 upon h, And so you are getting this as negative of 1. That is f prime plus 0 is negative of 1. Just check it. Rather, it is f prime negative 0. So we will just have to, okay, so what I can do, that I can erase it, because this is f prime of plus 0. This will not come. So f prime plus 0, then you will have to go to this side. So limit h tend to 0, f of 0 plus h. 0 plus h means here plus h. You will have to come here. 6h and something. It is here. It is here. 2h cube minus 4h squared. So we will have to write 2h cube minus 4h square plus 2h minus 0, f0 0 is all right, and upon h. So limit h tend to 0, when you write, everything cancels, because this is 2h cube by h minus limit h tend to 0, 4h square by h. The only power is here. 2 limit h tend to 0, h by h. So that number is in fact 2. So in fact, f prime 0 plus is 2. We record it here. F prime 0 plus is 2. Same definition tells you f prime negative 0 is limit h tend to 0, f of 0 minus h minus f of 0 upon negative h, mind you, negative h. So h tend to 0, f minus h. This time f minus h, if you write, then it is defined as fx is negative of x here. So you will get here negative of h upon negative h. So limit h tend to 0, negative of h by h. So that you will get as negative 1. It means you are getting that both right hand and left hand derivative exist, but they are not equal. They are finite, of course. They exist, so finite. So 2 and negative 1. So we will say that f is not differentiable. So f is not differentiable at origin, that is x equal to 0, origin x equal to 0. And also f prime is 0, derivative is 0 at points 1 and 1 over 3 here, 1 and 1 over 3. So f prime is 0 at x equal to 1 over 3 and 1. And all these points, all these points are interior to the interval minus 1 comma 2 closed. Everything lies inside. 1 by 3 lies inside, 1 lies inside, 0 lies inside. So it means we have found that this function has 3 critical points. 3 critical points. 3 critical points, namely 1 over 3, 1 and 0. So these 3 critical points are there because they are all lying interior. Out of them, derivative does not exist at origin, 0, and derivative is 0 at other 2 points, 1 by 3 and 1 by 1, both are inside. So there are 3 critical points, and n points, of course, are minus 1 and 2. By the way, we could have also found this one, second method, like this. That second method, simply what I will do, come back here, see, this is your expression, these two. So second method I can write here only. Second method, better I write here. Second method, I will just write limit of derivative. So I'll take limit x tend to 0 plus f of x, f prime of x, and I will take limit x tend to 0 minus f prime of x. So if you take limit to 0 plus f prime of x, 0 plus, then it means you want here this one. So this limit becomes 2. And if you want this one, this constant, this limit becomes 1, as we got earlier. So it means because limit exists, so you can say that f prime plus 0 is 2 and f prime negative 0 is minus 1. It is very shorter here because they exist. If they exist, then I have told you before that limit of derivative equals the value of derivative. If limit of derivative exists finitely, then it is a boon for you. It's a blessings for you. You can quickly find out. Okay, so we have done critical points. So for this function, we wanted to find critical points. That is done. We want to find an absolute maximum, absolute minimum. So the method is, the recipe is that now this is done. Now the recipe is that, okay, compute now f at all the points, all critical points as well as end points. So make a table. So we have got x equal to 0. So values of x will be 0, 1 over 3 we got, and 1. And we can write also this one. So before that, let me write here before that negative of 1, because that is end point. This is end point, minus 1 and 2. This also is end point. And these all three are critical points, critical points. And of course, as you see, they're lying interior to the interval. Now I'll just find the value. So I'll calculate f minus 1, f0, f1 over 3, f1, f2, f negative of 1. If you go for f negative of 1, so negative 1 you can find from here. Definition is given to be negative of x, so you will get 1. So f negative of 1 will be 1. f0 already we got 0. f1 by 3 if you write, then 1 by 3 will be obtained after 0. This one here. Calculate this at 1 by 3. 2x cube minus 4x square plus 2x. So if you calculate 2x cube minus 4x square and plus 2x cube minus 4x square and plus 2x, you compute at x equal to 1 over 3. So that is 2 into 1 over 27 minus 4 by 9 plus 2 over 3. So I can compute it 27. This is 2 minus 12 and plus 18. So of course I will get this number as 8 over 27. So f1 3 8 over 27. f1 is quite simple. So f1 is 0 because 2 minus 4 plus 4, f1 is 0. And f2 is 2 times 8 minus 4 times 2 square and plus 2 into 2. This goes away, so it is 4. Now we have got all the values of f for at critical points and also boundary point. Among all these, the least is 0. So it means that the function has absolute minimum. Absolute minimum is for f, the absolute minimum for f, the absolute minimum is 0 and attained at x equal to 0 and x equal to 1. Both value it is attaining. So that's all right. That can be attained for many values. And absolute maximum is 4. And this is attained at x equal to 2. X equal to 2. So is that all right? Let's check it. So we got this f minus 1, 0, this. So out of these 5 values, so we got 0 as the least one. So 0 becomes the absolute minimum, attained at 2 points, 0 and 1. And 4 becomes absolute maximum, attained just 1 point, x equal to 2. If you check the character of function at x equal to 1 over 3, so x equal to 1 over 3, if you check 1 over 3, you will find that actually, of course, it is not absolute maximum because it is plain that it is less than 4. So that's no brainer. You will find, in fact, that x equal to 1 by 3 is a point of relative maximum, means local maximum. Relative maximum or local maximum, you will find local. And so we can check that this also is happening. So this is the example for the other part. This is a good example because it tells you about many more things that you could have otherwise thought. Okay, so once we have done this, then again let's use definition of absolute maximum or least value or absolute minimum. This is a JE problem. Given f of x is negative of, and such things keep coming, negative of x cube plus b cube minus b square plus b minus 1 over b square plus 3b plus 2, that is 0 less than or equal to x less than 1. And this is 2x minus 3 when 1 less than equal to x, and this is less than equal to 3. So we are defining from some 0 to 3. Now we are saying that find all b. Our job is to find all b element of R, of course, such that the function f has the least value at x equal to 1. It has the least value equal to 1. Looks quite big, but actually you can break it down. See, minus x cube plus something plus lambda. This is just a cubic. This is linear 2x minus 3. Now f1 is defined from here. So what we can do that we can just make a rough this one. This is x equal to 1 point. So f1 is nothing but negative of 1. So f1 is here negative of 1. This is negative of 1. After this one, it goes increasing 1, 2, 3. It goes increasing because of course this function is increasing because this is positive. And this one minus x cube, that's still decreasing function. So it comes from 0 and something 1. Now if you want that the least value should be given by this member, it means the question is how to join this function and something that comes from here this way, I don't care which way it comes, whatever curve is there, it should come here somewhere. So let's draw a line from here, vertical line. So if you want that the function should have absolute maximum minimum at this place, then the left side curve cannot come like this. If it comes like this, that's a problem. Then no absolute minimum. So it means that if you want it, then it can this is open because it is not defined for this branch. This branch is the branch 1 is got by right side. So the question is how should it alight or how should it land on this line? Then that answer is that if it is like this one, then the other curve should come. It could become either like this, or it could also be exactly lie on it. So it could come and fill its hole here. This can be there. So it means we will say that, so this is just, we are drawing like this. So let me draw one here, right here. So this is this kind of thing. So you are saying that, okay, what should happen that f of 1 minus to the left of 1. This is the notation for limit x tend to 1 minus f of x. Notation is only called f of minus 1. So you want that f of minus 1, this number should be greater than or equal to negative of 1. Because then it is either here or up. Then in both cases this becomes absolute minimum, because now there is no point, no value which is less than this value. So this is the condition you want to ensure f negative 1, f1 minus. Now f minus 1, value at 1. So this is limit minus 1. This limit is minus 1. So this is minus 1 plus that is lambda only. That is b cube minus b square plus b minus 1 upon b square plus 3b plus 2 greater than or equal to negative 1. Now these things will go away. So you will be left with b cube minus b square plus b minus 1 upon b square plus 3b plus 2 greater than or equal to 0. I can factorize this further. So this will be giving me b square plus 1, b minus 1. This is b plus 1, b plus 2 greater than or equal to 0. I can draw the number line. This is negative 2, negative 1, and 1. And mind you, this is in the denominator, so they can never be 0. And so this is not minus 2, no negative 1, both are open because it is denominator. And union, 1 can be closed because 1 is the numerator. So this is 1 to infinity. Be very careful about this sign, or this sign, and this sign, because mostly JEE asks you the number of points. If you make a mistake, if you write 1 while the answer was 1, then this point is lost. So you will lose your marks. So please be attentive. So this is what we got by writing f of x. Is it okay? Okay. Now let me do another type 1, which tells you little geometrically. So it's like, don't always rush for maximum minima by calculus. You can also use somewhat non-calculus approach if it is feasible. So the question is that find the volume. So it says, the question says find the volume of greatest cylinder that can be inscribed that can be inscribed in a cone of height h, and of course radius say r or something. Height h and radius also you say radius r. So we'll say that what is the maximum volume of cylinder that can be inscribed here. We can do it quite easily using AMGM and some geometry. So this is my diagram. This is what it looks like. Now it is like this here. So let me make some names, label it A, B, C. This point I'll call N. This point I will call M. That's good enough. And this point, say, I can call R. So now I will draw this diagram. This is A. So this is A. This is M. This is R. This is N. This is C. Now height of N, the height of cone is given to be H. Radius is of course NC, that is given to be R. I designate this height, this Mn, height of cylinder, as small h, variable of course, because you have to fit in the largest one, and this is also a small r. Because triangle AMR is similar to triangle ANC, we have ratio of heights, that is h minus h and upon h. So h minus upon h, and that equals r upon r. So I can write a small r in terms of capital R. So I can write a small r is 1 minus h by h times capital R. That is your small r. Now the volume of cylinder, that is pi r square h. So I can write pi 1 minus h by h whole square. So pi r square. So this is pi r square and times h. So that is h is here. Because h by h occurs, I can write this as pi r square capital H 1 minus h by h whole square and times h over h. I can do like this, h over h. Notice how cleverly I am dealing with h over h. Because h is fixed, I want to find out what fraction h must be of h, say 2 by 3, 4 by 11, what h by h must be to have largest possible cylinder in volume. So this is pi r square h, volume of this one. Nothing great, just pi r square h. So now once I do this one, 1 minus h by this whole square, this one, then I observe one thing, that this you leave. I want to minimize this number. So let h by h equal to t. So of course 0 less than t less than 1. It will be 0 less than t less than 1. T is 1, not possible, because you cannot possibly have the whole height, and 0 of course is trivial. So 0 less than t, in which case there is no cylinder. So 0 less than t less than 1. Now I want to minimize, say called gt. I want to minimize gt is 1 minus t square times t. I can use calculus, I can expand things, but let's use the much beautiful AMGM. So I want to use AMGM inequality. I know this is positive 1 minus t. What I write this, I write as this I will write as 4 times 1 minus t by 2 whole square t, which I can write 4 into 1 minus t over 2, 1 minus t over 2 times t. So I'm looking at it at product of 3 numbers, 1 minus t by 2, 1 minus t by 2 and t. These all are positive. This is positive. Of course, this also is positive, and t of course positive. They are positive. Now apply AMGM. So we will write 1 minus t over 2 plus 1 minus t over 2 plus t over 3. So this is the arithmetic mean left hand side of 3 quantities on the left side. This is greater than or equal to geometric mean, so cube root of 1 minus t by 2, 1 minus t by 2 times t. That will give you this number becomes just 1. So 1 over 3 greater than or equal to cube root of 1 minus t by 2 whole square times t. And so when I cube both sides, I will end up with 1 over 27 greater than or equal to 1 minus t over 2 square t. Cube is gone. This one. So here, this one, gt. This was my gt. So this gt is less than equal to, this is 4 is already here, 4 by 27, because we have found that this is less than equal to 1 by 27, means I can write this way. I have found 1 minus t by 2 whole square times t less than or equal to 1 over 27. Once that is done, then we can interpret the result. First of all, for what it is attained. For that, AMGM inequality gives the answer that for equality to hold, all of these numbers, all of these on which you are applying the must be equal. That is 1 minus t by 2 is 1 minus t over 2 is t. These two are anyway equal. So just equate 1 minus t over 2 equal to t. That gives you 1 minus t equal to 2t. That gives you 3t equal to 1. So t is 1 over 3. It means that t equal to 1 over 3 and t was h over h. So h by h is 1 over 3. It means if height is such that is 1/3 of the height of original cone, then you will say that this attains the maximum volume or greatest volume of the cylinder. And greatest volume is given by expression is here v cylinder. Let me write pi r square h. So v cylinder is pi r square h times 1 minus t square times t. Let's check again. 1 minus t square times t. This is t, and t is h by h. So it means you will say that this number, of course, we know that this is now 4 by 27. So you are saying that V maximum is pi r square h and times 4 by 27. So this is 4 by 27 times pi r square h. So it means the maximum volume of cylinder that can be inscribed in a cone of height h and radius r is nothing but 4 by 27 times pi r square h. You can also compare that how V cone and V maximum compares. So we know already that if you want to do this, then the volume of cone is 1/3 of pi r square h. So I can write this as 4 by 27 times 3 times 1/3 of pi r square h. So that is your 4 over 9. And this is volume of cone, this one. So we can say that V cylinder maximum happens, cone is of course fixed. So we can say that V cylinder maximum happens when height of the cylinder h is 1/3 of height of cone, so 1/3 of h. And also in that case, the volume of cylinder is 4 by 9ths of volume of given cone, because cone is fixed. So this way we say that, okay, we get the answer using just arithmetic mean and geometric mean inequalities. Although we could have used differentiation to find 1 minus t square t, I could have written gt. I could have done this as 1 minus 2t plus t square times t. I could have written t cube minus 2t square plus t and differentiated. But then that's not as good as AMGM. So whenever opportunity is there, please use AMGM first, AMGM, then some geometrical argument. Then if they don't work, then you go to calculus arguments. Normally you won't need many times calculus argument. You would need only for those problems which involves e to the power x or some crazy functions where, of course, by very definition, by very design, you can't use some good techniques of AMGM or even geometrical techniques. Okay, so that's all. Let me stop sharing now.